Somewhere above you tonight, hidden inside the constellation Ophiuchus, an invisible object is quietly holding an entire star in its grip. It doesn't glow, it doesn't explode. If you pointed the world's best telescope directly at it, you would see nothing at all. Just an ordinary sun-like star, orbiting something that isn't there. We only learned this in 2022. It sits 1,560 light-years away, close enough in galactic terms to be called our neighbor. But here's the part almost everyone gets wrong. Being the nearest black hole and being reachable are not the same thing, not even close. Tonight, we calculate it properly, honestly, carefully, with our fastest machines, our best physics, and our most patient assumptions. If you enjoy deep space and slow science, hit that like button and subscribe to the channel. It genuinely helps this channel grow, and there's much more like this coming. Make yourself comfortable. Let's begin. For most of human history, we didn't know where the nearest black hole was. Not because we weren't looking, because black holes, by their very nature, refuse to be found the easy way. Most of the black holes astronomers had catalogued before 2022 were what's called X-ray binaries. These are black holes locked in orbit, with a companion star close enough that the black hole is actively stealing gas from its surface. That stolen gas doesn't fall in quietly. It spirals inward, heating to millions of degrees, screaming out X-rays before it disappears past the point of no return forever. Those X-rays are how we've found black holes for decades. The black hole itself stays invisible. The violence around it gives it away. But most black holes, astronomers had long suspected, don't behave that way at all. Most of them form the ordinary way a massive star dies. It exhausts its fuel. It collapses under its own weight. And if there happens to be a companion star nearby, that companion often orbits at a safe, comfortable distance, far enough that nothing gets stolen, nothing heats up, nothing screams, no feeding, no X-rays, no fireworks of any kind. Just two objects, one visible and one not, circling each other in complete silence for millions of years, unnoticed. These are called dormant black holes, and by their nature, they don't announce themselves. They don't glow. They don't call attention to themselves in any way at all. They simply are. That should sound reassuring. A black hole that isn't doing anything. It isn't. Because dormant doesn't mean harmless. It means undetectable. A dormant black hole has exactly the same mass, exactly the same gravity, exactly the same crushing finality waiting at its center as one that's actively feeding. The only difference is that one advertises itself and the other hides in plain sight, sitting somewhere in the sky above you right now, giving away nothing. So how do you find something whose entire strategy is to not be found? You don't look for it directly. You look for what it's doing to something else. Finding a dormant black hole means finding an absence. It means proving something is there by watching the thing next to it move in a way that only makes sense if something invisible is tugging on it. A star wobbling ever so slightly off a straight line, for no visible reason at all. That's exactly what happened in 2022. An international team led by astrophysicist Kareem El-Badry, working with the Harvard-Smithsonian Center for Astrophysics and the Max Planck Institute for Astronomy, was combing through data from the European Space Agency's Gaia spacecraft, a mission whose entire purpose, since its launch in 2013, has been extraordinary precision. Gaia measures the positions of well over 1 billion stars in our galaxy. It tracks their motion across the sky with a precision fine enough to catch a wobble, so small it would be invisible to almost any other instrument ever built. Out of the hundreds of thousands of candidate wobbles buried in that data, one stood out. A star, roughly the mass and temperature of our own sun, was orbiting something with about 10 times the sun's mass. And that something gave off no light, no X-rays, no detectable trace of any kind, just gravity, acting on nothing anyone could see. To confirm what they were looking at, the team turned to some of the largest telescopes on Earth. The Magellan Clay Telescope in Chile, the Gemini North Telescope in Hawaii, the Keck 1 telescope also in Hawaii. Each new observation tightened the case a little further. Whatever this sun-like star was orbiting, it wasn't another star. A companion that massive would have been bright enough to see with ease. There was nothing, just an empty patch of sky, and a star behaving exactly the way physics predicts it would behave next to a black hole. They named it Gaia BH1. Now picture what that object actually is. A black hole with a mass around 9.6 times that of our Sun, compressed down into a point so dense that not even light can escape it once crossing a certain boundary. Its companion star, ordinary, sun-like, unremarkable in every other way, orbits it once every 185.6 days, at a distance almost exactly equal to the distance between Earth and our own Sun. Imagine our solar system, quietly rearranged. The Sun still there, still warm, still shining, exactly as it always has. But in the place where Earth should be, nothing. A black hole instead of a planet, holding a calm, well-behaved, perfectly ordinary star in a slow and stable orbit, the way our own Earth circles our own Sun. Somewhere, right now, that pairing is turning in the dark, exactly like clockwork, and has been for longer than anyone can say. For context, astronomers estimate our galaxy alone may contain something like 100 million black holes. Almost all of them dormant, like this one. Almost all of them invisible to every instrument we currently have pointed at the sky. Gaia BH1 isn't unusual because it exists. It's unusual only because, for once, we happened to catch it. And here is the detail that matters most for tonight. Gaia BH1 sits about 1,560 light-years from Earth. In the scale of our galaxy, a disk stretching roughly 100,000 light-years across. That is remarkably close. It is, right now, the nearest confirmed black hole we know of anywhere. But nearest is a word that means something very different in astronomy than it does anywhere else in life. It doesn't mean nearby. It doesn't mean within reach. It means only this, the smallest number we currently have. And the smallest number, in this case, is still large enough to make the idea of actually visiting it feel almost absurd. So let's not leave that as an abstraction. Let's measure it, not in light years, which are easy to say and almost impossible to feel, but in something closer to a felt distance. Miles, years, the lifespan of everything you have ever known. Because once you see what 1,560 light-years really means, stripped of the shorthand, the word nearest is going to feel very different by the time we're done. A light-year sounds like a unit of time. It isn't. It's a unit of distance. The distance light travels in a single year, moving at roughly 186,000 miles every second. Light is the fastest thing in the universe. Nothing with mass has ever matched it, and as far as we currently understand physics, nothing with mass ever will. So when we say Gaia BH1 is 1,560 light-years away, we're saying something very specific. We're saying that even traveling at the maximum possible speed the universe allows, it would take light itself over 15 centuries to make that crossing. Sit with that for a second. Look up at Gaia BH1 tonight, if you had a telescope powerful enough, and you would not be seeing it as it is now. You would be seeing light that left that system around the year 466 of the modern calendar. That light began its journey during the final decades of the Western Roman Empire, in the reign of the Byzantine Emperor Leo I. It has been crossing the galaxy ever since. Uninterrupted, silent, alone, it was already in flight through the fall of Rome, already in flight through the rise and fall of empires on every continent, already in flight when someone first pressed ink to paper with a printing press, when someone first pointed a telescope at the sky, when the first airplane left the ground, when the first spacecraft left Earth entirely. None of that touched it. It just kept moving in a straight and silent line through all of it. And it is only now, this year, quietly arriving at your eyes. That is what 1 light year of separation actually buys you in delay. Now multiply that delay by 1,560. 1 light year is approximately 5.88 trillion miles. Multiply that by 1,560, and the distance between Earth and Gaia BH1 comes out to roughly 9.17 quadrillion miles. 9 million billion miles. A 9 followed by 15 zeros. Numbers that large stop meaning anything on their own. So let's compare it to something already almost incomprehensible. The nearest star to our Sun, Proxima Centauri, sits about 4.24 light-years away, a distance so vast that our fastest current spacecraft would take tens of thousands of years just to reach it. Gaia BH1 is roughly 368 times farther than that. If reaching our nearest stellar neighbor already sits at the outer edge of what feels achievable, Gaia BH1 sits centuries of additional travel time beyond even that horizon. Here's another way to feel the scale, and it might be the strangest one yet. Our entire Milky Way galaxy is about 100,000 light-years across, edge to edge. Gaia BH1, at 1,560 light-years away, is still deep inside our own galactic neighborhood. It hasn't even begun to approach the galaxy's edge. We are not talking about leaving the Milky Way. We are not talking about crossing to another galaxy, the way Andromeda sits 2.5 million light-years distant, an entire separate island of stars. We are talking about a target that, by galactic standards, is essentially in our own backyard. And that backyard is 9 quadrillion miles wide. That's the part that should stop you. Not that Gaia BH1 is far. Everything in space is far. It's that this is supposed to be the close one. The nearest black hole we've ever found, out of an estimated 100 million scattered across our galaxy, still sits at a distance that makes nearest feel like a technicality rather than a comfort. The words nearest and close have almost nothing in common once you're speaking at this scale. Gaia BH1 earns the word nearest only because everything else we know of happens to be even farther away. It does not earn the word close by any standard a human being would recognize, standing on the surface of the Earth, looking up. Let's put one final, human-scale anchor on it. If you could somehow compress the entire 9.17 quadrillion-mile journey down to the distance between New York and Los Angeles, roughly 2,450 miles, then the width of a single human hair, held up against that same shrunken scale, would represent a distance larger than the entire orbit of Pluto around our Sun. Read that again slowly because it's worth it. At that scale, our whole solar system, the Sun, every planet, every orbit out to Pluto and beyond, becomes smaller than something you could lose between your fingers. And the gap to Gaia B H1 is still the entire cross-country trip. That is how small our solar system becomes, and how large the gap to Gaia B H1 remains, even after compressing it down to something a person could hold in their mind. Distance alone is already staggering, but a number on a page, however large, is still just an abstraction. It doesn't yet tell you anything about whether the trip is actually possible. For that, we need to introduce something with an engine. We need to ask what would carry a traveler across that gap, and just how fast the fastest thing humanity has ever built can actually go. Because there is a fastest thing, we've already built it, and it's about to answer this question in a way you might not expect. So what do we actually have? What is the fastest thing human beings have ever built, and how does it hold up against 9 quadrillion miles? Let's start with the spacecraft most people have actually heard of. Voyager 1 launched from Cape Canaveral in 1977, sent out to study Jupiter and Saturn before continuing onward, indefinitely, into interstellar space. It succeeded beyond anything its engineers could have promised. In 2012, Voyager 1 became the first human-made object to cross the heliopause, the boundary where the sun's solar wind finally gives way to the pressure of true interstellar space. It is, right now, the most distant human-made object in existence, still transmitting, still traveling, after nearly 50 years of uninterrupted flight. 50 years, no repairs, no refueling, just drifting outward, faithfully, into the dark. Voyager 1 moves at roughly 38,000 miles per hour relative to the Sun. That's fast enough to circle the entire Earth in under 40 minutes. Fast enough that if you fired it from New York, it would reach Los Angeles in under 4 minutes. By any everyday human measure, this is an extraordinary speed. On the scale of interstellar distance, it is close to standing still. Let's do the honest math. At 38,000 miles per hour, covering the 9.17 quadrillion miles to Gaia B, H1 would take approximately 27.5 million years. Say that number slowly because it doesn't fully land the first time. 27.5 million years is roughly 137 times longer than modern humans, Homo sapiens, have existed as a species. For Voyager 1 to have any chance of arriving by now, it would have needed to launch not in 1977, but back when our ancestors were still evolutionarily distinct from chimpanzees. 27.5 million years is longer than most mammal species have existed at all, start to finish, before quietly going extinct. So our most famous spacecraft, humanity's furthest flung achievement, isn't even in the conversation. But Voyager 1 isn't our fastest machine anymore. That title now belongs to something built for a completely different mission. NASA's Parker Solar Probe wasn't designed to travel far. It was designed to travel close, dangerously close, to the Sun itself, using a specially engineered carbon composite heat shield to survive temperatures exceeding 2,500 degrees Fahrenheit. To get there, the probe performs a series of gravity-assist flybys of Venus, each one tightening its orbit, slinging it faster and faster around the Sun with every pass. On December 24, 2024, Parker Solar Probe made its closest approach yet, passing within roughly 3.8 million miles of the Sun's surface. At that moment, caught in the full pull of the Sun's gravity, it reached a confirmed top speed of 430,000 miles per hour. The fastest any human-made object has ever traveled. For context, that speed would carry you from New York to London in about half a minute. It sounds unstoppable. It sounds like the number that changes everything. It doesn't. Let's apply that speed, our single fastest achievement in the entire history of spaceflight, to the distance ahead of us. At 430,000 miles per hour, sustained the entire way, the trip to Gaia BH1 would take approximately 2.43 million years. Modern Homo sapiens have existed for roughly 300,000 years. Even using our single fastest object in history, moving continuously in a straight line, which Parker Solar Probe actually can't do, since its speed comes entirely from diving close to the Sun's gravity, not from independent thrust. The journey would still take about 8 times longer than our entire species has existed. And that's the best case scenario. That's the fastest thing we've ever built, moving at its single fastest recorded moment, applied to the whole distance without ever slowing down. Picture it launching at the very beginning of our species. If Parker Solar Probe had left Earth at that speed roughly 300,000 years ago, when the first members of our species appeared in East Africa, it would still have over 2 million years left to travel. Right now, tonight, still in transit. It would not arrive before every single human being who has ever lived, every civilization that has ever risen and fallen, every war, every book, every discovery had already happened and been quietly forgotten. This is not a failure of ambition, it's arithmetic. Distance and speed, multiplied honestly, simply produce a number too large for better engineering alone to close, not with the propulsion physics we currently understand. And that raises the obvious next question. Parker Solar Probe reaches its top speed only briefly, only by falling toward the Sun's gravity. It isn't built to sustain that speed on its own, and it certainly isn't built to accelerate past it. So what would it actually take, in terms of engines, in terms of fuel, in terms of propulsion systems humanity hasn't built yet, to construct something that could? That's where this gets genuinely uncomfortable. To understand why speed alone doesn't solve this problem, it helps to understand what actually pushes a spacecraft forward, and why every method we currently have runs into a wall long before it reaches anything close to the speeds this journey would demand. Start with the most familiar option, chemical rockets. This is how every crewed mission in human history has left the ground. The Saturn V that carried Apollo astronauts to the moon, the Space Shuttle, the rockets launching satellites into orbit today. Chemical rockets work by burning fuel and expelling the exhaust at high speed out the back. And by Newton's third law, that push in one direction creates an equal push in the other. Engineers trust chemical rockets because they work, they're reliable, they're well understood, tested across 7 decades of spaceflight, refined down to the smallest bolt. But trust isn't the same as capability. The reason comes down to something called specific impulse, essentially, how efficiently a propulsion system converts fuel into thrust. Chemical rockets have among the lowest specific impulse of any propulsion method we use, which means they need enormous amounts of fuel to achieve even modest speed increases. To get faster, you need more fuel. But that additional fuel has its own mass, which means you need even more fuel just to carry the fuel you already added. The relationship isn't linear, it compounds. This is why rockets are mostly fuel by weight, and why chemical propulsion tops out at speeds nowhere near what interstellar distances demand, no matter how large you build the rocket, no matter how much you're willing to spend. So chemical propulsion is out. What's next? A more efficient alternative already exists, and it has already flown. Ion propulsion, used successfully by NASA's Dawn spacecraft on its mission to the asteroid belt, works on a completely different principle. Instead of burning chemical fuel, it uses electric fields to accelerate charged particles, typically xenon gas, out of the engine at extremely high velocity. Ion engines are remarkably fuel efficient, using a tiny fraction of the propellant a chemical rocket would need for the same change in speed? That sounds like the answer. It isn't. The efficiency comes at a cost: thrust. An ion engine produces force comparable to the weight of a single sheet of paper resting in your hand. Dawn's ion engine took nearly 4 days of continuous firing just to accelerate from 0 to 60 miles per hour. Over months and years, that gentle, patient push does add up to meaningful speed. But even scaled up, even run continuously for years on end, ion propulsion, using technology we've actually built and flown, not theorized, still tops out at speeds far short of what would meaningfully shorten a multi-million-year journey. 2 real technologies down, both genuinely impressive, both nowhere close. So consider a third option, one that has never flown but has been seriously studied: nuclear propulsion. In the late 1950s and early 1960s, a group of physicists, including Freeman Dyson and Ted Taylor, worked on a concept called Project Orion, a spacecraft propelled by detonating small nuclear explosives behind it, with a massive pusher plate absorbing each blast and converting it into forward thrust. On paper, Orion's designers calculated potential speeds far beyond anything chemical or ion propulsion could reach, theoretically enough to make a journey to a nearby star conceivable within a human lifetime, at least at the outer edges of the concept. It's a strange thing to picture: a spacecraft riding a chain of small nuclear detonations further and further into the dark, propelled by its own controlled violence. Project Orion was never built. The Partial Test Ban Treaty of 1963, which prohibited nuclear explosions in space, effectively ended the program, along with serious unresolved questions about radioactive fallout, structural stress on the pusher plate, and the sheer number of nuclear devices the mission would actually require. It remains to this day a theoretical concept, studied, calculated, never tested at scale. And even if we set aside the political and safety obstacles entirely, even if we imagine Orion had been built exactly as designed, the honest math still falls short. The most optimistic nuclear pulse propulsion estimates from that era topped out at speeds representing only a small, single-digit percentage of the speed of light. That would meaningfully shorten a journey to a nearby star. It would not meaningfully shorten a journey of 1,560 light-years. At even 5% of light speed, a figure well beyond what Orion's own designers believed achievable, the trip to Gaia B-H1 would still take over 31,000 years. 3 technologies, one flown for decades, one flying right now, one studied for years by serious physicists and never built at all. All 3 share the exact same limitation. They are extraordinary compared to standing still. They are nowhere close to what this particular distance demands. So suppose, for the sake of argument, that propulsion itself was never really the obstacle. Suppose we imagined the most efficient theoretical engine physics allows, one that could genuinely push a spacecraft to a meaningful fraction of the speed of light. Even then, a second wall appears, and this one has nothing to do with engineering at all. It's a wall made of pure energy, and the numbers behind it are even less forgiving than anything we've covered so far. Here is the uncomfortable truth sitting underneath every propulsion discussion we've just had. Even if engineering were somehow solved completely, even if we built the perfect engine with perfect materials and perfect fuel, physics itself imposes a second, deeper limit. And this one has nothing to do with what we can build. It comes from the basic relationship between energy and mass, and it doesn't care how clever our designs become. Albert Einstein's special theory of relativity, published in 1905, gave us the equation most people can at least recognize. E equals mc squared. Energy equals mass, multiplied by the speed of light, squared. What that equation quietly implies is something most people never actually sit with. As an object moves faster and faster, approaching the speed of light, the energy required to keep accelerating, it doesn't increase in a simple, proportional way. It increases sharply, disproportionately. The closer you get to light speed, the worse it gets. Getting a spacecraft to 50% of the speed of light takes a large amount of energy. Getting that same spacecraft to 90% of the speed of light takes dramatically more. Not twice as much, but far beyond that. Getting it to 99% takes more still. The curve doesn't rise gently the way you might expect. It climbs towards something like a wall, because as an object's velocity approaches the speed of light, the energy required approaches infinity, not a large number. Infinity. Consider what that means for propellant. Every method of propulsion we understand, chemical, ion, even the theoretical nuclear pulse concepts from Project Orion, works by carrying mass with you and expelling it behind you. But if you want that spacecraft to reach a significant fraction of light speed, the amount of propellant mass required, using known chemistry, becomes larger than the spacecraft could physically carry. Not impractically large, physically impossible to carry, because the fuel itself has mass. And accelerating that fuel to relativistic speed requires energy proportional to its own mass, which requires more fuel to carry that energy, which has its own mass, which requires more fuel again. The problem feeds itself, endlessly, until the math simply collapses under its own weight. This isn't a hypothetical difficulty, it's arithmetic. The same compounding fuel problem we saw with chemical rockets, except now applied at a scale where even our best theoretical designs collapse under their own energy requirements. So, if ordinary propellant can't do it, what could? There is, in theory, one substance efficient enough to matter: antimatter. When matter and antimatter meet, they don't just react. They annihilate each other completely, converting the entire mass of both into pure energy. The most efficient energy release physics allows. In principle, a small amount of antimatter could power a spacecraft far closer to relativistic speed than any chemical or nuclear method ever could. It sounds like the answer we've been looking for this whole time. Here is where theory runs headfirst into the unforgiving reality of what we can actually produce. Antimatter does not occur naturally in usable quantities anywhere in our solar system. It has to be manufactured, one subatomic particle at a time, inside facilities like CERN's Large Hadron Collider. And the quantities we've managed to produce, across the entire history of particle physics, are measured not in pounds, not in ounces, but in billionths of a gram. Nanograms produced at enormous energy cost, existing only briefly before being stored in specialized magnetic traps, because antimatter destroys itself and its container on contact with ordinary matter. To put this in human terms, powering a meaningful interstellar mission with antimatter would require quantities measured in kilograms. What humanity has actually managed to produce and store across every particle accelerator ever built in the history of our species amounts to a fraction of a single grain of sand's worth of mass. We are not close. We are not approaching close. We are standing at the very first theoretical step of a propulsion method that remains, for now, almost entirely outside our engineering capability. The energy problem, then, isn't a matter of needing better materials, or a bigger budget, or a few more decades of research. It's a mismatch between what physics demands and what humanity, at its current level of technological development, can actually produce. The gap isn't measured in years. It's measured in orders of magnitude we haven't yet found a path across, and may not for a very long time. Suppose, though, that this problem too was somehow solved. Suppose some future civilization built a spacecraft with an energy source powerful enough and propellant efficient enough to genuinely approach a meaningful fraction of light speed. The ship exists. The physics somehow works. There is still one more problem waiting inside it. And this one isn't made of metal or math or fuel. It's made of something far more fragile. It's made of the human body itself. Suppose every problem we've covered so far were solved. Suppose a future civilization built a spacecraft with impossible propulsion and impossible energy reserves, capable of genuinely approaching a meaningful fraction of light speed. There is still one more obstacle standing in the way, and it has nothing to do with engines or fuel. It's the traveler. The human body did not evolve for space. It evolved for Earth, for one specific gravity, one specific atmosphere, one specific level of background radiation that our bodies have spent hundreds of thousands of years quietly adapting to. Remove any single one of those conditions for long enough, and the body begins, quietly and measurably, to fail. Start with bone density. NASA's decades of data from the International Space Station show that astronauts in microgravity lose bone mineral density at a rate of roughly 1 to 1.5% per month, concentrated in the weight-bearing bones, the lower spine, the hips, the legs. That's a rate of loss more than 10 times faster than what a person with severe osteoporosis experiences on Earth over the same span of time. On a 6-month stay aboard the ISS, that adds up to as much as 10% of bone mass in the hardest hit regions. Full recovery after return to Earth can take 3 to 4 years, if it happens completely at all. Now stretch that timeline. A journey lasting years, decades, or, as we've calculated, millions of years, isn't simply a longer version of a 6-month mission. It's a fundamentally different problem. Even with continuous resistance exercise, the best countermeasure we currently have, bone and muscle loss in microgravity has never been fully halted, only slowed. The body a traveler would need to survive the destination is not the same body that could survive the journey to reach it. Radiation compounds the problem further. Here on Earth, we're shielded by two things: our planet's magnetic field, which deflects charged particles from the sun and from deep space, and our atmosphere, which absorbs most of what gets through. Astronauts aboard the ISS, still tucked inside Earth's magnetic field, receive relatively modest radiation exposure. Leave that protection, and the numbers change quickly. NASA's Curiosity rover carried an instrument called the Radiation Assessment Detector, which measured the radiation environment during its 253-day cruise to Mars in 2011 and 2012. The data showed an average dose rate of approximately 1.8 millisieverts per day during that interplanetary transit, meaning the cruise phases alone, for a round-trip Mars mission, would expose a crew to roughly 0.66 sieverts of radiation. For context, the European Space Agency generally limits an astronaut's total career radiation dose to 1 sievert, a threshold associated with roughly a 5% increase in lifetime fatal cancer risk. A single round trip to Mars, using current technology, would consume most of that lifetime allowance in under 2 years of travel. Now imagine a journey measured not in months, but in millions of years, outside any planetary magnetic field, exposed continuously, every single day, to galactic cosmic rays with no atmosphere and no shield. That isn't a radiation risk that better engineering gradually reduces. It's an exposure level that no human body, and likely no biological body of any kind, built from any material we understand, could reasonably be expected to survive. So no single human traveler could make this journey alive. Not one. Regardless of how well the ship performed, regardless of how perfect the propulsion, regardless of anything. Which means the problem quietly shifts. Not a faster ship, a self-sustaining one. A vessel carrying not one crew, but many generations of crew. Each raising the next, none of whom would ever see the destination. Each one living and dying entirely inside a sealed, artificial world. Generation folding into generation, for longer than recorded history has existed. We've actually tested a smaller version of that idea. Once, on Earth. In 1991, a research facility in Arizona called Biosphere, two sealed 8 researchers inside a fully enclosed, self-contained ecological system, designed to recycle its own air, water, and food indefinitely, cut off entirely from the outside world. It was meant to run for 2 years. It didn't go the way anyone planned. Within months, oxygen levels inside the sealed structure began dropping unexpectedly, eventually falling low enough that supplemental oxygen had to be pumped in just to keep the researchers safe, quietly breaking the experiment's central promise of total self-sufficiency. The cause turned out to be an imbalance in the facility's soil microbiology, consuming more oxygen than the plant life inside could replace. That experiment lasted 2 years, on Earth, with a support team standing by, ready to intervene the moment something went wrong. A true generational ship would need to solve that same problem of ecological balance, indefinitely, with no support team, no ability to open a door and step outside, no room for error of any kind, for a span of time longer than our entire species has existed. Even setting radiation and bone loss aside, even solving the ecological question completely, one more layer still remains. Time dilation, the strange, real, relativistic effect that near light-speed travel would introduce, is sometimes proposed as a kind of shortcut for a problem exactly like this. It isn't a shortcut. And to understand why, we need to look honestly at what actually happens to time itself as an object approaches the speed of light, and at what would be waiting at the other end of this journey, assuming anything ever arrived at all. There is one piece of physics that sometimes gets misunderstood as a loophole in everything we've covered so far. Time dilation. It's real. It's been measured, tested, and confirmed repeatedly since Einstein first described it in 1905. And it's worth understanding honestly because it does change part of this story, just not the part most people hope it will. Special relativity tells us that time does not pass at the same rate for everyone. It passes more slowly from an outside observer's perspective for anything moving close to the speed of light. The faster you go, the more pronounced the effect becomes. At half the speed of light, time for a traveler passes about 13% slower than it does for someone standing still, watching from Earth. At 90% of light speed, that gap widens dramatically. The traveler experiences time passing at less than half the rate of the outside universe. At 99% of light speed, the traveler's clock runs more than 7 times slower than Earth's. Now apply that to the Gaia BH1 journey specifically. If a ship somehow reached 99% of the speed of light and sustained it, the trip would still take about 1,576 years, measured from Earth. But for the people aboard the ship, protected by time dilation, only around 222 years would actually pass. Push the ship further, to 99.9% of light speed. Earth still measures roughly 1,562 years elapsing. The sheer distance barely allows for anything less. But the crew aboard would experience something closer to 70 years. Still a full human lifetime. Still longer than anyone could realistically survive under the radiation and biological conditions we just walked through. Time dilation compresses the traveler's experience of the journey. That much is true, and it's genuinely strange and beautiful physics. But it does nothing to reduce the energy required to reach those speeds in the first place. And it does nothing at all, to slow the number of years ticking by for every single person left behind on Earth. It isn't a shortcut, it's a trade. The ship's crew might personally experience a survivable span of subjective time. But by the time they arrived, more than 15 centuries would have passed back home. Everyone they knew and the entire civilization they left behind would already be gone. Not far away. Gone. And suppose, despite everything, the propulsion, the energy, the biology, the radiation, the impossible engineering, the 15 centuries lost behind them, a traveler actually arrived at Gaia BH1. What would be waiting for them? A black hole doesn't have a surface. What it has is an event horizon, the boundary beyond which nothing, not even light, can escape its gravity. For a black hole with the mass of Gaia BH1, roughly 9.62 times that of our Sun, we can calculate the exact size of that boundary using Einstein's equations. The math gives us what's called the Schwarzschild radius. For this particular black hole, approximately 28.4 kilometers. Think about that for a moment. An object nearly 10 times heavier than our entire Sun, and its event horizon is smaller than most cities. That extreme compression is exactly what makes the region just outside the horizon so violent. Gravity's strength depends heavily on how close you are to the source, and near a small, dense object like this, gravity doesn't just get stronger as you approach. It gets stronger at wildly different rates across very short distances. This creates what astrophysicists call tidal force. If a traveler approached feet first, the gravitational pull on their feet would be measurably, catastrophically stronger than the pull on their head, just a couple of meters away. Run the numbers for Gaia BH1's horizon, and that difference in pull comes out to something like 22 million times the force of gravity you feel standing on Earth right now, acting across the length of a single human body. Astrophysicists have an informal name for this process: spaghettification. And for a black hole this size, it wouldn't happen gradually, the way you might picture it. It would happen long before reaching the horizon at all, stretching anything made of ordinary matter into a thin, elongated stream well before arrival. But here's something worth pausing on, because not every black hole behaves this way. Sagittarius A star, the supermassive black hole at the center of our own galaxy, has a mass around 4.3 million times that of our Sun. And because its mass is spread across a proportionally much larger event horizon, the tidal forces at its boundary are, by comparison, almost gentle. A traveler could theoretically cross the horizon of a black hole, that large without being torn apart at all, at least by tidal forces alone. Gaia BH1 is not that kind of black hole. It is small, it is dense, it is stellar in origin, and its gravity punishes anything that gets close in the most literal, physical sense possible. So even in the most generous version of this thought experiment, a ship with impossible propulsion, impossible energy, a crew that somehow survived millions of years of biological decay, arriving after 15 centuries have already passed on Earth. The destination itself offers no arrival at all. Only a final, violent transition into something physics can describe. but no observer could ever survive to report on. Every angle we've examined so far has been about the ship, or the crew, or the destination itself. But there's one more angle left, and it isn't about physics at all. It's about us, about whether any human institution, any civilization, could actually sustain a project on a timescale this long, even if every single scientific obstacle simply disappeared tomorrow. There's one more angle left, and it's the strangest one, because it isn't really about physics at all. It's about time. Not the relativistic kind we just walked through, but the human kind. The question of whether any civilization, any institution, any continuous human effort could actually sustain a project across a timescale long enough to matter here. Human beings are not naturally built for long projects. Most of what we build to be finished within a single lifetime, often within a few years. Bridges, buildings, careers, entire technologies rise and fall within a single human generation, sometimes within a single decade. But history does offer a small number of genuine exceptions. Projects deliberately built to outlast the people who started them. Consider Cologne Cathedral in Germany. Construction began in 1248 under Archbishop Conrad von Hochstaden, intended as a worthy home for relics believed to belong to the biblical three kings. It was an extraordinary undertaking, even by medieval standards. Soaring Gothic towers, intricate stonework, a structure meant to inspire awe for centuries to come. But construction didn't proceed smoothly, or continuously, or quickly. Funding dried up. Interest waned. Around 1560, work stopped almost entirely, leaving a massive unfinished crane sitting atop one incomplete tower for nearly 300 years, a landmark of its own kind, a visible symbol of an unfinished promise, standing silent against the sky for generation after generation. Construction didn't resume in earnest until the 1840s. The cathedral was finally completed in 1880, 632 years after the first stone was laid. No single person who began that project lived to see its end. No single generation did. It took roughly 20 human generations, working, stopping, forgetting, rediscovering, and finally finishing what strangers centuries earlier had started, without ever meeting them, without ever knowing their names. 632 years is, by any human measure, an almost unimaginable span for a single continuous project. And it is, against the number we're actually working with tonight, essentially nothing. The distance to Gaia BH1, even under our most optimistic propulsion assumptions, demands a timescale measured not in centuries, but in millions of years. To put that in perspective, Cologne Cathedral's 632 years would need to repeat, in full, more than 3,800 times over. Back to back, without a single interruption, just to match the 2.43 million years our fastest recorded spacecraft speed would require. 3,800 cathedrals, each one taking longer to build than anything else our species has ever deliberately sustained. Laid end to end, just to equal one leg of this journey. We have made smaller, more deliberate attempts to think on longer timescales. In 1995, computer scientist Danny Hillis proposed something he called the 10,000-year clock, a mechanical timepiece designed to keep accurate time for 10,000 years with minimal maintenance, built as a physical symbol to encourage long-term thinking. The Long Now Foundation, which Hillis co-founded in 1996, alongside Stuart Brand and musician Brian Eno, has spent decades building a full-scale version of that clock deep inside a mountain in West Texas, funded substantially by Amazon founder Jeff Bezos. It's an extraordinary act of intentional patience. An engineering project explicitly designed to function for longer than any human civilization in recorded history has yet endured. 10,000 years is the most ambitious timescale any human institution has ever deliberately committed to building for. And 10,000 years is still only a fraction of 1% of the journey time to Gaia BH1. Even our most patient, most future-minded engineering, stretched to its philosophical limit, falls short of this distance by a factor of hundreds. What this reveals, in the end, isn't only a problem of propulsion, or energy, or biology, or the crushing tidal forces waiting at the destination. It's continuity itself. No government has lasted this long. No language has remained unchanged this long. No religion, no institution, no unbroken chain of human memory has ever stretched across a span of time even remotely close to what this journey would require. A ship capable of surviving the trip wouldn't just need better engines. It would need to survive the complete rise and fall of civilizations, repeated over and over, thousands of times, while somehow still remembering where it was going and why it ever left in the first place. This is where the numbers stop behaving like a series of individual obstacles and start becoming something closer to a single, quiet fact about the universe and our place inside it. We are extraordinarily good, as a species, at solving problems that fit inside a human lifetime. We build cathedrals across centuries when we're at our most patient. We measure our proudest achievements in decades, sometimes in a few hundred years if we're being unusually ambitious. And the distance to the nearest known black hole simply exists on a different order of time altogether. Not more difficult, the way a hard problem is difficult. Different in kind, the way a distance and a duration are different kinds of things entirely. So we're left, finally, not with a plan, or a proposal, or a countdown to some future mission. We're left with a number large enough that it stops behaving like an obstacle to be solved, and starts behaving like a fact of the universe to simply sit with, the way we sit with the size of the ocean, or the age of starlight, or the certainty of an ending we will never personally witness. Let's come back, one more time, to the light. Somewhere above you right now, in the direction of the constellation Ophiuchus, photons are arriving that left Gaia BH1's companion star during the reign of the Byzantine Emperor Leo I, in the 5th century, while the Western Roman Empire was living out its final, uncertain decades. That light has been traveling, uninterrupted, in a straight and silent line for the entire span of everything that came after. It was already halfway here when the printing press was invented. It was already halfway here when the first telescope was pointed at the sky. It has been in transit longer than every empire that has ever risen and dissolved into history. Longer than every language that has been spoken and forgotten. Longer than any single human memory could ever hold. And it is only now, tonight, touching whatever's left of it down onto Earth. We spent this whole hour measuring what stands between us and that black hole. 9 quadrillion miles, millions of years at our fastest recorded speed. A body that fails long before the journey ends. Tidal forces at the destination measured in the tens of millions of times the pull you're feeling right now. Simply lying still, simply breathing. None of that was exaggeration. Every number was real, calculated honestly, checked against what physics and biology and history actually tell us. And all of it points toward the same quiet conclusion. Gaia BH1 will remain, for the foreseeable future of our species, a place we can only ever measure, never visit, never touch, never stand within 1,000 miles of, and live to describe it. There's something worth sitting with in that. Not defeat exactly, something closer to scale. We are used to thinking of distance as an inconvenience, as something bridged, eventually by faster planes, better roads, more efficient rockets. Most of the distances human beings have ever crossed have, sooner or later, yielded to enough time and enough patience. But some distances were never meant to be crossed at all. Some distances exist simply to be understood, measured, calculated, and then quietly set down, the way you might set down a stone too heavy to carry any farther, resting it gently in the grass and walking on without it. Gaia BH1 sits there right now, in the dark, 10 times heavier than our sun, and yet completely invisible. Holding a sun-like star in a slow, patient, 185-day orbit that has likely continued unchanged for longer than our species has walked upright. It doesn't know it's the nearest black hole. It doesn't know it was found in 2022, or that a handful of astronomers spent months confirming its existence with some of the largest telescopes on Earth. It doesn't know that tonight, 1,560 years after its light began this journey, someone somewhere is lying in the dark, eyes closed, listening to a voice describe the impossible distance between here and there. It simply sits and orbits and bends the light of its companion, the way it has for longer than any of us can meaningfully picture, and the way it will continue to, long after every voice describing it has gone quiet, long after this very recording has been forgotten. We are very small, and very slow, and very short-lived, measured against a thing like that. But we are also, somehow, the only part of this entire equation capable of noticing it at all. 9 quadrillion miles of empty space, a black hole with no surface and no light of its own. Tidal forces that would end anything soft enough to feel them. And somewhere in the middle of all that vastness, a species evolved just enough curiosity and just enough patience to point an instrument at the dark and measure something it will never reach. That, in the end, might be the only kind of arrival that was ever actually possible. Not a ship crossing the distance, just understanding, quietly closing the gap that nothing else ever could. You are listening to these words from somewhere on a small, warm planet, orbiting an ordinary star, in a galaxy that contains, by some estimates, 100 million black holes like the one we've spent this hour describing. Almost all of them invisible, almost all of them silent, and the nearest one we've ever found still sits far enough away that light itself needs 15 centuries just to make the crossing. Walk outside some clear night if you can, and look toward the constellation Ophiuchus. You won't see Gaia BH1. It has no light of its own to show you. But somewhere in that patch of sky, a sun-like star is quietly circling something that isn't there, the way it has for longer than human history, and it will keep doing so long after tonight is forgotten. We are not built to reach it. Our bodies fail. Our fuel runs out before our will does. Our civilizations rise and dissolve on timescales too short to matter against the distance involved. And yet we found it anyway, measured it, named it, calculated exactly how far out of reach it truly is. That too is a kind of achievement, not arrival, understanding. Picture a single candle, lit in a room the size of a continent. That's the light of one star, against the true scale of the dark it sits inside. Gaia BH1 is not even the flame. It's the absence right beside it, invisible, patient, real. There is nothing you need to do with any of this tonight. No number to remember, no fact to hold on to until morning. The black hole will still be there tomorrow, and the night after that, turning slowly in the dark, whether you're awake to think about it or not. It has never once needed anyone's attention to keep existing. It simply continues, the way it has for longer than any calendar can measure, the way it will, long after every voice that ever described it has gone quiet. So let it go now. Let the numbers blur. Let the distance stop meaning anything in particular. Somewhere above you, a star is still circling something invisible, exactly as it has for 1,500 years, exactly as it will for 1,500 more. Patient, silent, entirely unconcerned with whether anyone down here is still listening. You don't have to be. The nearest black hole in the universe is still farther away than anything you will ever hold, and it always will be. Rest now.